These L'Hopital's rule problems are borrowed straight from the College Board, so they are very similar to what you might find on the AP exam. If you appreciate the content, please give it a like. Example 1. Find the limit as x approaches 0 of 1 minus cosine 2x over 5x. Before we can do L'Hopital's rule, we have to do direct substitution and see if we get 0 over 0 or infinity over infinity. Plugging in 0 right here, the cosine of 0 is 1, and 1 minus 1 is 0. Obviously, if you plug in 0 right here, you get 0 in the denominator as well. It is mandatory that you write arrow 0 before you use L'Hopital's rule. If the numerator and denominator are both approaching 0, or if they are both approaching infinity, L'Hopital's rule says you can take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. So let's do that. The derivative of 1 is 0, so that's nothing. The derivative of cosine is negative sine. So the negative is going to cancel out the negative that's already there, so it's going to turn positive. So we will have the sine of u, which is 2x. But we have to do the chain rule and then multiply by the derivative of the inner function, which is 2. Meanwhile, the derivative of 5x is 5. If we do direct substitution now, the sine of 0 is 0. So the numerator is approaching 0, while the denominator remains a constant 5. 0 over 5 is 0, so that's the limit. Pause the video and try to do example 2 by yourself. If we do direct substitution in the numerator, the natural log of 1 is 0. Plugging in 1 right here, we get 1 minus 1, which is also 0. You must write arrow 0 before proceeding with L'Hopital's rule. Taking the derivative of the numerator and the denominator will not change the value of the limit. So let's do that. Here's a memorized rule for your flashcards. The derivative of natural log x equals 1 over x. So in the numerator we have 1 over x. The derivative of x squared minus 1 is 2x. Let's do direct substitution again and see what we get. In the numerator, if we plug in 1 right here, we have 1 over 1, which is 1. In the denominator, if we plug in 1 right here, we get 2. 1 over 2 is 1/2. So that's the limit. Example 3. The table above gives selected values of a twice differentiable function f of x. Find the limit as x approaches 3 of f at 2x minus 1 over x squared minus 9. Direct substitution, plugging in 3 for x, gives us 6 minus 1, which is 5. So the numerator is approaching f at 5, which according to the table is 0. Of course, if we plug in 3 right here, that's going to give us 9 minus 9, which is also equal to 0. Since the numerator and denominator are both approaching 0, we can proceed with L'Hopital's rule, but you must show this part. This is mandatory. According to L'Hopital's rule, we can take the derivative of the numerator and denominator without changing the value of the limit. We're going to have to do the chain rule in the numerator. First, we take the derivative of the outer function, which is f prime. The inner function is 2x minus 1. And according to the chain rule, we have to multiply by the derivative of the inner function, which is 2. The derivative of the denominator is 2x. Let's try the direct substitution again. I'm going to put this little 2 here in the front. If we plug in 3 right here, that's 6 minus 1, which is 5. So we'd have 2 times f prime at 5. According to the chart, f prime at 5 is 7. And of course 2 times 7 is 14. Meanwhile, if we plug in 3 right here, that's going to be 6. So 14 over 6. This reduces to 7 over 3. So that's the limit. Pause the video and try to do example 4 by yourself. If we plug in 0 for x right here, e to the 0 power is 1. Cosine of 0 is also 1, so that's 1 minus 1. Plugging in 0 right here gives us 0, and 1 minus 1 minus 0 is 0. So the numerator is approaching 0. Obviously, if we plug in 0 here and here, we get 0. Since the numerator and denominator are both approaching 0, we can use L'Hopital's rule and take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. So let's do that. Here are 2 flashcards for you. The derivative of e to the x is e to the x. The derivative of cosine x is negative sine x. The extra negative will turn this negative into a positive. And the derivative of negative 2x is negative 2. Dropping to the denominator, the derivative of x squared is 2x, and the derivative of negative 2x is negative 2. Let's see what happens if we do direct substitution now. Plugging in 0 for x right here, we have e to the 0, which is 1. The sign of 0 is 0. And then we have the minus 2. So that equals negative 1. Plugging in 0 right here gives us 0 minus 2, which equals negative 2. So the limit is negative 1 over negative 2, which is positive 1/2. So the answer is C. For example 5, we must find the limit as x approaches infinity. So we can't just do direct substitution, we have to ask ourselves what happens to the numerator and denominator as x increases without bound. Well, as x gets bigger and bigger, this first term gets bigger and bigger. So does the second term. So the input is getting bigger and bigger. The graph of natural log x looks like this. As the input value increases without bound, natural log x also increases without bound. So the numerator is approaching infinity. Obviously, as x approaches infinity, the denominator approaches infinity. Since both the numerator and denominator approach infinity, we can apply L'Hopital's rule. We can take the derivative of the numerator and the denominator without changing the value of the limit. The derivative of natural log u is 1 over u times u prime. So here we go. The derivative of natural log u is 1 over u. So that's 1 over, let me change colors here, e to the 3x plus x. So that's our u times u prime. The derivative of e to the u is e to the u times u prime. So the derivative of e to the 3x is e to the 3x times the derivative of 3x, which is 3. The derivative of x is 1. So this is the u prime that we have to multiply. I'm going to put it in the numerator. Everything you see here in red is the derivative of the numerator. The derivative of the denominator is 1. We don't really need this 1, so I'm going to erase the 1 and sort of shift everything down. This limit is equivalent to the original limit. Let's think about what happens to the numerator and the denominator as x increases without bound. Well, that means 3x increases without bound. So this term gets bigger and bigger. So the numerator is approaching infinity. Similarly, the denominator is approaching infinity. This gets bigger and bigger, and x itself gets bigger and bigger. Since the numerator and the denominator are both approaching infinity, we have to keep going by applying L'Hopital's rule again. we can again take the derivative of the numerator and the denominator without changing the value of the limit. The derivative of e to the 3x is e to the 3x times 3, but there's already a 3 there, so it'll be 3 times 3, which is 9. The derivative of 1 is 0, so that's gone. Dropping to the denominator, the derivative of e to the 3x is e to the 3x, chain rule, times 3. And the derivative of x is 1. Let's imagine what happens to the numerator and the denominator as x increases without bound. Well, this gets bigger and bigger, so the numerator approaches infinity. And this gets bigger and bigger, so again, the denominator approaches infinity. So guess what? We have to keep going by doing L'Hopital's rule again. So let's take the derivative of the numerator and the denominator, which will still not change the value of the limit. The derivative of e to the 3x is e to the 3x times 3, but there's already a 9 there, so 9 times the extra 3 will be 27. Dropping to the denominator, the derivative of e to the 3x is e to the 3x times 3, but there's already a 3 there, so 3 times 3 is 9. The derivative of 1 is 0, so we have this. But wait, before we think about what happens to the numerator and the denominator as x increases without bound, we suddenly notice that we have this e to the 3x in the numerator and the denominator that will cancel each other out. We are left with 27 over 9, which equals 3. So the answer is C. Before we move on, let me mention a common mistake that I often see. Many students want to cancel out e to the 3x here and here. But you cannot cancel out things that are connected by addition or subtraction, so you cannot cancel these out. Similarly, on the red step, you cannot cancel out this e to the 3x with this e to the 3x. Because of the plus 1, these cannot be canceled out either. It's only when you get to the purple step and there's no more addition and subtraction that you can finally cancel these out. Example 6 is a great problem from an old AP exam. It ties together several concepts that we've learned so far in AP Calculus. There's a lot going on, so buckle up. The functions f and h are twice differentiable with h at 2 equal to 4. The function h satisfies h of x equals this expression for x not equal to 2. It is known that the limit as x approaches 2 of h can be evaluated using L'Hopital's rule. Use the limit as x approaches 2 of h of x to find f at 2 and f prime at 2. Show the work that leads to your answers. First, focus on this statement right here. F and h are twice differentiable. That means that f prime and h prime exist, as do f double prime and h double prime. Quick side lesson, differentiable implies continuous. If a function is differentiable, it has to be continuous because you can only take the derivative of a continuous function. If h of x is continuous, it is specifically continuous at x equals 2. I'm mentioning that because this whole problem is about h at 2 and the limit as x approaches 2. Arguably, the most important thing we learned from Unit 1 was the definition of continuity. If h of x is continuous at x equals 2, that means the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right, which is equal to the value of h at 2. I tried to drill this into your head back in Unit 1. However, this was the long way of writing the definition of continuity. It was very useful for solving problems back in Unit 1. However, if the limit from the left is equal to the limit from the right, these two statements can be combined into the single statement, the limit as x approaches 2. Because the limit as x approaches 2 automatically means the limit from the left and the limit from the right. So if h of x is continuous at x equals 2, It means the limit as x approaches 2 of h of x is equal to h at 2. Just to recap, if h is differentiable everywhere, that means h is continuous everywhere, including at x equals 2. So according to the definition of continuity, that means the limit as x approaches 2 of h of x is equal to the value of h at 2. On the next step, I'm going to substitute this expression for h of x right here. Also, we know that h at 2 is equal to 4, so I'm going to substitute that value right here. So now we have this equation, which we somehow need to solve for f at 2 and f prime at 2. We are told that this limit can be evaluated using L'Hopital's rule. But L'Hopital's rule only works if the numerator and the denominator are both approaching infinity or both approaching 0. In the numerator, direct substitution gives 4 minus 4, which is equal to 0. For L'Hopital's rule to apply, the denominator must also approach 0. In other words, direct substitution, plugging 2 in for x right here, should give us 0 for the answer. So let's do that side quest. 1 minus f at 2 to the third power should equal 0. Adding f at 2 cubed to both sides of the equation will sort of move this over to the right. So we get 1 is equal to f at 2 cubed. And then if we take the cube root of both sides, we get 1 is equal to f at 2. Well, this is one of the things we were looking for. We just found that f at 2 is equal to 1. Kabam! We have solved half of the problem already. But let's get back to the blue. We are evaluating this limit using L'Hopital's rule, which says we can take the derivative of the numerator and the denominator without changing the value of the limit. By the way, it is mandatory that you show the arrow 0, arrow 0. The derivative of the numerator is 2x, and the derivative of 1 is 0. For the rest of the denominator, we need to apply the chain rule. So first we take the derivative of the outer function, which is negative 3 parentheses to the second power. But we have this inner function, f of x. And the chain rule demands that we now multiply by the derivative of the inner function. So we multiply by f prime of x. We should be able to evaluate this limit by direct substitution. So let's plug in 2 for all of these x's. So now we have this equation. Notice the f of 2 right here, but we just found that f at 2 is equal to 1. So let's make that substitution. Plugging in 1 for f at 2 gives us this expression in the denominator, and 2 times 2 is 4. All of this is equal to 4. So now we have this equation. We have already found f at 2. We still need to find f prime at 2. Notice that's sitting right here. So we just need to solve this equation for f prime at 2. We can solve this by cross multiplication, which you guys love to do. So I'm going to sort of think of this as 4 over 1. So if we cross multiply, if we multiply along this diagonal, 4 times negative 3 is negative 12. 1 squared is just 1, which I will not write. So we have negative 12 times f prime at 2 is equal to the other diagonal. 4 times 1 is 4. We can get f prime at 2 by itself by dividing both sides by negative 12. 4 divided by negative 12 is negative 1/3. And that's it. We found f at 2, which equals 1, and f prime at 2, which equals negative 1/3. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.